large height, h, and then we drill a hole in the bottom with diameter d, which is much less than h, and we want to approximate the rate at which water is flowing out. So, plus the pressure divided by the density. Of course, this operates under a few assumptions. First, that our liquid is incompressible, so density is constant. Second, that it's steady state, which means nothing is changing other than time. Over time, the velocity can't change, this can't be rotating, nothing. So that's exactly why this is an approximation. This doesn't really work in practical scenarios where things change a lot over time. But since this is a very small hole, understandably, the level of water is not going to go down by a lot, which means that it's approximately going to be steady state. So this says that this is equal to 0. Or, in simpler terms, that this whole thing is constant over time. So now, let's try and solve for that velocity. So you get u is equal to, well, you got to bring all these to the other side. So you get half u squared is equal to c minus p over rho plus gz. This will be plus. And now all we have to do is multiply by 2 on both sides and square root. Now here's the thing. First of all, we're trying to look at how fast water is flowing out. So we're going to choose some of the water at the top of the reservoir, which means at the height h. So we're going to substitute h in for z. And that's where we're going to find the velocity, u. So in other words, we're kind of finding how fast the water level is going down. So what's going on here? Well, this term looks a little bit nasty, but here's the thing. P over rho is tiny, really tiny, especially when you're dealing with regular air and regular water. This is, which looks intimidating, but this is, of course, which gives and when we multiply by 2, always. Meanwhile, what happens if we plug in h equals 50 and z is equal to 10, for example? This already practically totally destroys the influence of this. And then when you consider just how big h is in respect to d, this could be as big as, say, 500. Well, no, that's like Burj Khalifa levels. This could be maybe even 100 meters tall, for example. Sorry, why would I add it? So this completely dwarfs this term. And another consideration to make, of course, is that this term cancels it out. Well, approximately, at least. So this is approximately equal to the square root of negative 2gh. All right. Now, let's look at what happens if we just we take some water in a glass and we pour some of the water that was in that glass out of the glass. And the glass is a height h above the ground. And we want to see what is the velocity of the water when it hits the ground. Well, conservation of energy. the initial potential is equal to the final kinetic energy. So you get mg big H is equal to half mu squared. Cancel out the m on both sides, and you get that u is equal to the square root of 2gh. So why are these two so similar? Well, you can think of it this way. Because of how small the hole is, essentially, let's use the main diagram, essentially, we can just focus on everything directly above the hole, as if it was a little tube, and all of the water was being channeled through that tube, with basically no interruptions. Now, of course, new water is going to get in the way and slow it down a little bit, which is, of course, why this modifier exists, to mess our path up. But overall, because of how small this hole is, we can approximate this as a tube, and this tube is going to operate off of the same velocity as water spilling out of a cup from a height h, the square root of 2gh. So that's exactly why the intuition and the math behind why the flow rate out of this hole is approximately the square root of 2gh. Thanks for watching.